Evolution unleashed nightmares that would make even the fiercest T-Rex seem tame by comparison, and they ruled Earth tens of millions of years before dinosaurs ever appeared. Picture this: oceans ruled by creatures with circular saw mouths and grasping facial claws, forests dominated by walking cacti armored in spines, rivers patrolled by 8-foot sea scorpions with crushing pincers, and floodplains stalked by saber-toothed proto-mammals that could open their jaws wide enough to swallow your head whole. These weren't movie monsters. They were real animals that hunted, killed, and dominated Earth's ecosystems for millions of years before vanishing into extinction's abyss. This is the story of evolution's most terrifying experiments. Predators so alien, so perfectly designed for killing, and so utterly unlike anything alive today that their extinction feels less like tragedy and more like salvation. From the Cambrian seas, where nightmare hunters first evolved eyes to see their prey, through coal swamps stalked by creatures that defied every rule of nature, to the late Permian floodplains where saber-toothed killers perfected the art of the precision strike, we'll explore the horrifying reality of prehistoric life before dinosaurs. These creatures didn't just die out. They were erased by mass extinctions, outcompeted by even deadlier designs, or trapped by their own terrifying specializations. Their stories reveal a darker side of evolution, nature's relentless drive to create ever more efficient killing machines, and the brutal reality that even the most fearsome predators can become extinct overnight when the world changes beneath them. The circular saw predators of the Cambrian seas. Radiodonts redefined what it meant to be a predator in Earth's ancient oceans. These weren't small, simple hunters. They were the first true apex predators, massive animals that could reach over a meter in length when most other creatures barely measured in centimeters. The most famous, Anomalies, combined features so alien that when scientists first discovered its fossils, they thought they were looking at 3 different animals. The frontal grasping appendages were labelled as shrimp. The circular mouth was identified as a jellyfish. The body segments were classified as sea cucumbers. Only decades later did paleontologists realise these pieces belonged to a single, terrifying predator, unlike anything in modern oceans. The defining feature that made radiodonts true nightmare fuel was their mouth structure. Instead of jaws, they possessed a circular ring of overlapping plates arranged like the blades of a pineapple slicer. This structure could open and close in a rotating motion, creating a spiraling saw that could slice through flesh with horrifying efficiency. For years, paleontologists believed this mouth was strong enough to crack the hard exoskeletons of trilobites, turning radiodonts into the ocean's shell-crushing juggernauts. Recent biomechanical studies paint a different but equally disturbing picture. The mouth plates, while sharp and numerous, weren't reinforced for crushing. Instead, they excelled at precision cutting, slicing through soft tissues, severing muscle attachments, and creating wounds that would cause prey to bleed out rapidly. Their hunting strategy was equally sophisticated. Those frontal appendages weren't just for show. They were multi-purpose killing tools. CT scans of radiodont fossils reveal complex joint systems that allowed these appendages to grab, sweep, probe, and manipulate prey with shocking dexterity. In Anomalies, these arms curved inward and ended in rows of sharp spines arranged like the teeth of a bear trap. The predator would use them to snatch swimming prey mid-water, pin struggling animals against the seafloor, or probe into crevices where smaller creatures tried to hide. The appendages could move independently, giving radiodonts a level of manual control unprecedented in the Cambrian world. They weren't mindless eating machines. They were calculating hunters with the tools to exploit every weakness in their prey. The terror didn't stop at their weapons. Radiodonts possessed some of the most advanced sensory systems of the Cambrian period. Their eyes contained up to 30,000 individual lenses, providing high-resolution vision that could detect even subtle movements in murky water. This visual acuity meant prey had nowhere to hide. A trilobite trying to remain motionless on the seafloor, a worm attempting to blend into sediment, or a small arthropod drifting in the water column, all were visible to radiodont eyes. Combined with their swimming ability, this made them the ocean's first sight-based pursuit predators, capable of spotting prey from a distance and running it down with relentless efficiency. Their bodies were engineered for speed and stamina. Along each side, radiodonts possessed overlapping swimming flaps arranged in sequential rows. These flaps undulated in smooth, wave-like motions that propelled them forward with surprising grace and power. Modern cuttlefish use similar propulsion, but radiodonts perfected the technique 500 million years ago. Fossil beds show these predators lived in areas with strong currents, environments where only the fastest swimmers could thrive. They didn't ambush prey from hiding spots. They chased it down in open water, using superior speed and maneuverability to close the distance before deploying their grasping appendages and circular saw mouths. But radiodonts weren't just lone killers. Recent discoveries have revolutionized our understanding of their ecological roles. Some species, like Tamisiocaris, evolved into filter feeders with elongated, comb-like appendages that resembled baleen plates. These gentle giants swam through plankton clouds with mouths agape, straining tiny organisms from the water. This means radiodonts diversified into multiple feeding strategies. Apex predators, scavengers, and filter feeders all coexisted under the same evolutionary umbrella. The Cambrian oceans contained radiodont species filling nearly every aquatic niche, from shallow coastal waters to deeper offshore environments. The true horror of radiodonts lies in what they represented. Evolution's first successful experiment in creating large, mobile, sensory-dependent predators. Before radiodonts, animals were small, slow, and poorly equipped to hunt actively. After radiodonts appeared, the evolutionary arms race exploded. Prey species evolved harder shells, faster swimming, better camouflage, and defensive spines. The entire structure of marine ecosystems shifted from passive grazing to active predator-prey dynamics. Radiodonts didn't just hunt, they fundamentally changed how life worked in the oceans. Their extinction came gradually as the Cambrian gave way to the Ordovician. New predators emerged: early jawless fish with better armor, cephalopods with jet propulsion and grasping tentacles, and arthropods with more efficient body designs. Trilobites evolved tougher exoskeletons that radiodonts couldn't penetrate. Prey became scarce as competition intensified. Filter-feeding radiodonts faced disruption to plankton communities as ocean chemistry shifted. Predatory species struggled in increasingly complex reef environments where their open-water hunting tactics became less effective. The world that radiodonts dominated, simple, open seas filled with soft-bodied or lightly armoured prey, gradually transformed into something they couldn't navigate. Their circular saw mouths and grasping arms, once the ultimate killing tools, became relics of an evolutionary era that had passed them by. The walking nightmare cacti of ancient seafloors. Hallucigenia earned its name honestly. It looked so bizarre that scientists spent decades reconstructing it backwards and upside down, creating images that seemed pulled from fever dreams rather than Earth's fossil record. This creature belonged to the Lobopodians, a group of worm-like animals with stubby legs that crawled across Cambrian seafloors more than 500 million years ago. But calling them simple worms fails to capture the sheer strangeness of their designs. These animals sported rigid spines jutting from their backs, armoured plates covering their bodies, and bizarre feeding appendages that looked like nothing in the modern world. They transformed the ocean floor into a landscape of walking horrors. The original reconstruction of Hallucigenia placed it as an otherworldly balloon animal floating through ancient seas. Scientists positioned the spines downward as walking stilts, and the soft legs upward as waving tentacles. This inverted creature looked so impossible that it perfectly embodied the chaos of early animal evolution. Only in the 1990s did researchers flip it right side up, placing the legs down and spines up. Then, in 2015, high-resolution imaging finally revealed its head, a bulbous structure with a simple mouth ringed by tiny teeth. Each correction made hallucigenia slightly less nightmarish, but it remained deeply unsettling. A tube-like body covered in defensive spines, crawling on stubby legs that seemed barely adequate for the task. What made Lobopodians truly horrifying was their role as evolutionary testing grounds for arthropod features. These creatures mixed traits from modern velvet worms, early arthropods, and completely extinct lineages into combinations that defy easy categorization. Hallucigenia had soft, unjointed legs like velvet worms, but also carried rigid spines that hinted at external armor. Microdictyon, another Lobopodian, developed distinctive net-like plates along its sides. Not quite the segmented exoskeleton of true arthropods, but a clear experiment in protective plating. Colonial, nicknamed the walking cactus, took spine coverage to terrifying extremes, with its entire body bristling with defensive projections, while long, delicate feeding appendages extended from its head like sensory whips. The spines weren't decorative, they were survival equipment. The Cambrian seas swarmed with radiodonts and other emerging predators that had developed increasingly efficient killing strategies. Soft-bodied animals became easy meals. Lobopodians responded by evolving external defenses, testing different spine arrangements, plate configurations, and body shapes to find combinations that would deter attacks. Hallucigenia's paired rows of spines created a hedgehog-like profile that made it difficult to grab or swallow. Colonium's dense spine coverage turned it into an ambulatory pincushion. These defenses came at a cost. Spines added weight and reduced flexibility. But in a world where radiodonts prowled with grasping claws, the trade-off made sense. Recent discoveries from China's Zhenjiang biota reveal Lobopodians were far more diverse than early fossil finds suggested. Some species had multiple sets of feeding arms extending from their heads, creating multi-limbed horrors that could manipulate food while walking. Others developed elaborate mouth cones with rings of tiny teeth arranged in spiral patterns. Some had eye stalks that protruded from their heads, giving them periscope-like vision while their bodies remained hidden in sediment. This diversity shows Lobopodians weren't following a single evolutionary playbook. They were trying everything simultaneously, throwing dozens of body plan variations at the problem of survival and seeing what worked. One particularly important discovery involves claw-like structures at the ends of Lobopodian legs. Microscopic analysis shows these claws consisted of stacked proteins remarkably similar to the claw materials in modern arthropods. This suggests that arthropod limbs didn't suddenly appear fully formed, but evolved gradually from simpler structures. Lobopodians served as the testing phase, developing proto-claws that could grip and anchor, but lacked the sophistication of true arthropod appendages. Their legs could hold onto surfaces and secure prey, but couldn't manipulate objects with the precision that later arthropods achieved. They represented evolution's rough draft of the features that would eventually dominate animal life on Earth. Their lifestyle was equally strange. Most Lobopodians moved slowly across the seafloor, scraping organic material from microbial mats, or hunting tiny prey hidden in sediment. Their narrow, tube-like bodies let them squeeze into tight spaces between rocks or burrow partially into soft mud. This slow, methodical existence made armor essential. They couldn't outrun predators, so they had to endure attacks. Species that lacked adequate defenses disappeared quickly from the fossil record. Those that survived into the Middle and Late Cambrian showed increasingly elaborate protective features. But elaborate defenses couldn't save Lobopodians from obsolescence. By the Late Cambrian and early Ordovician, true arthropods had evolved segmented bodies, hardened exoskeletons, and fully jointed limbs. These improvements provided better mobility, stronger protection, and greater adaptability to different habitats. Arthropods could swim, crawl, burrow, and eventually even walk on land. Lobopodians, constrained by their simple body plans and limited mobility, found themselves outcompeted in nearly every environment. Their soft tissues and stubby legs became liabilities in a world dominated by animals with superior engineering. Most Lobopodian lineages died out, leaving only distant relatives in obscure corners of modern ecosystems. Today's velvet worms and tardigrades carry faint echoes of Lobopodian body plans, but they're tiny, limited to specific microhabitats, and bear little resemblance to their Cambrian ancestors. The walking nightmare cacti that once dominated seafloors vanished almost completely, remembered only through fossils preserved in fine-grained rocks. Their legacy lives on in the arthropods that inherited Earth. Insects, crustaceans, arachnids, and countless other species all carry refined versions of features that Lobopodians first tested. But the original experiments, those spine-covered horrors that crawled through Cambrian seas, are gone forever. The armoured slugs with saw-blade tongues. Waiwaxia and the Halkyrheids represented evolution's early attempts at creating mobile armour, living tanks that crawled across Cambrian sea floors protected by overlapping scales and defensive spines. These creatures looked like someone had crossed slugs with medieval chainmail, creating animals that seemed more mechanical than biological. They appeared during the Cambrian explosion when predators were rapidly evolving new killing strategies, and soft-bodied animals faced extinction unless they developed defences. Waiwaxia and Halkyrheids answered that challenge with some of the most innovative protective structures in early animal evolution, but their solutions proved temporary. They thrived briefly, dominated their ecological niches, then vanished completely, leaving no living descendants and only fossilised hints of their bizarre anatomies. Waiwaxia, discovered in Canada's Burgess Shale, looked like a flattened oval slug covered in rows of leaf-shaped scales called sclerites. These sclerites overlapped like roof shingles, creating flexible armour that protected the animal's soft interior while still allowing movement. Each scale locked into the adjacent scales through precise fitting, forming a continuous defensive surface. The armour wasn't rigid like a shell. It flexed and shifted as Waiwaxia crawled, maintaining protection while preserving mobility. Along the creature's sides and back, long spines projected outward at angles, creating a porcupine-like profile that discouraged attacks from radiodonts and other predators. Any predator attempting to grab or bite Waiwaxia would encounter spines first, making the effort painful and potentially dangerous. The underside of Waiwaxia was entirely soft and unarmoured, revealing its slug-like nature and showing the early stages of a muscular creeping foot similar to modern mollusks. But the real surprise came when scientists examined its feeding structures. Waiwaxia possessed a pair of hooked, scraping elements inside its mouth that resembled early versions of the radula, the tongue-like organ covered in tiny teeth that modern mollusks use to rasp algae from rocks and shred food. These scraping tools weren't as sophisticated as true radulae, but they served a similar function, allowing Waiwaxia to scrape organic material from surfaces and process food more efficiently than animals with simple mouths. This radula-like structure has sparked fierce debates in paleontology. Was Waiwaxia an early mollusk experimenting with specialised feeding tools? Or was it part of a completely separate lineage that independently evolved similar structures through convergent evolution? The evidence remains ambiguous. Some fossils show feeding elements simpler than true radulae, suggesting Waiwaxia represented a parallel experiment. Other fossils show enough similarity to indicate a possible direct connection. Either way, Waiwaxia demonstrated that evolution was testing specialized feeding strategies in multiple lineages simultaneously, exploring different ways to exploit the rich microbial mats that covered Cambrian seafloors. Halkyrheids took the armoured slug concept in a different direction. Instead of oval and flat like Waiwaxia, Halkyrheids had elongated slug-like bodies with armour arranged in two major sclerite zones running along each side. These overlapping plates formed genuine chainmail coverage, flexible yet protective. But the most distinctive features were the two hard shells positioned at the front and back of the body, small cap-shaped shields that protected the creature's head and tail. This three-part design, shell, armor, shell, fascinated scientists because it resembled the arrangement seen in chitons, modern mollusks that also have repeating armor plates. Yet Halkyrides weren't direct ancestors of chitons. They were parallel experiments exploring similar protective strategies, but heading down an evolutionary branch that would eventually dead end. The structure of Halkyrid sclerites provides crucial clues about their biology. Each scale showed growth patterns, tiny pits and lines indicating the armor was continuously maintained and modified as the animal aged. Their shells displayed growth rings similar to early brachiopods and mollusks, but with subtle differences in composition and structure. This mixture of traits earned Halkyrides the label mosaic organisms, creatures combining features from multiple animal groups without clearly belonging to any. They were evolutionary prototypes testing combinations of protection, soft bodies, and slow movement in ways no living animal replicates. Both Waiwaxia and Halkyrides lived in ecosystems increasingly dominated by predation. The Cambrian explosion had produced radiodonts, large arthropods, and even small predatory worms learning to bite, crush, or scrape prey from the seafloor. In this dangerous new world, armor became one of the most valuable survival strategies. The success of Waiwaxia and Halkyrides during the early and middle Cambrian demonstrates how crucial protective structures had become. But as predators continued evolving, the arms race intensified. Radiodonts developed stronger appendages and more efficient killing techniques. Arthropods evolved crushing mouthparts. The flexible armor that initially protected these armored slugs gradually became insufficient against increasingly sophisticated attacks. Their extinction was gradual but inevitable. Predators evolved stronger jaws capable of piercing or crushing sclerite armor. Some learned to flip armored prey over, exposing the soft, vulnerable undersides. Others developed tactics to break individual scales, creating weak points that could be exploited. At the same time, more advanced mollusks appeared with thicker, more solid shells rather than scales. These solid shells provided better protection with less weight and complexity. Arthropods refined their exoskeletons into jointed, articulated armor that offered both protection and mobility. Waiwaxia and Halkyrides, with their intermediate designs, found themselves outclassed on both fronts. By the Middle Cambrian, populations were already declining. Their fossils become increasingly rare in younger rock layers, suggesting they were losing ground to better adapted competitors. By the Ordovician, they had disappeared entirely. The armored slug experiment ended, leaving behind only fossils and evolutionary lessons. Their designs may have been too specialized to adapt when ecosystems shifted, or perhaps they simply couldn't compete with animals that refined the concepts they pioneered. True raduli appeared in more advanced mollusks. Proper segmented shells developed in articulated brachiopods. Stronger exoskeletons emerged in arthropods. The innovations hinted at by Waiwaxia and Halkyrides found fuller expression in other lineages, while the original innovators vanished into extinction's void. The 8-foot sea scorpions that ruled prehistoric waters. Eurypterids earned their nickname sea scorpions through sheer nightmare-inducing appearance, elongated bodies, segmented tails, powerful pincers, and large compound eyes set on flat, shield-like heads. These weren't actually scorpions, but they evoked the same visceral fear response. They first appeared in the Ordovician period and reached their peak during the Silurian, dominating rivers, lakes, bays, and shallow seas for over 200 million years. Before sharks and bony fish evolved into apex predators, Eurypterids held the crown as the ocean's most fearsome hunters. Some species like Jacalopterus reached over 8 feet in length, making them the largest arthropods ever to exist. Their rise represented arthropod predation at its absolute peak, and their fall marked the end of an era when invertebrates could compete with vertebrates for control of aquatic ecosystems. The front of a Eurypterid's body was engineered for killing. The first pair of limbs often ended in powerful pincers that could grab, crush, and tear prey with devastating efficiency. These weren't simple claws. They were articulated weapons with serrated edges and precisely calculated leverage points. Fossil evidence shows some Eurypterid pincers could exert enough force to crack the shells of smaller arthropods or puncture the armour of early fish. The remaining limbs served multiple functions: walking along the bottom, digging through sediment, or in many species, the last pair evolved into wide paddles that functioned as underwater propulsion systems. These paddle limbs let Eurypterids manoeuvre with surprising agility, combining the ambush capabilities of a bottom-dwelling predator with the pursuit abilities of an open-water hunter. Their telsons, the tail-like structures at the rear, varied dramatically between species, suggesting different hunting strategies and habitats. Some Eurypterids had broad, paddle-shaped telsons used for swimming and steering. Others possessed sharp, spike-like telsons that may have served defensive purposes or helped anchor the animal while feeding. A few species had telsons with elaborate shapes, suggesting specialized functions that paleontologists still debate. This anatomical diversity shows Eurypterids weren't a single type of predator, but a whole family of designs, each optimized for specific prey and environmental conditions. Eurypterids possessed one of their greatest advantages in habitat flexibility. Unlike most marine predators, they weren't restricted to salt water. Fossil deposits show they thrived in freshwater rivers, coastal lagoons, tidal flats, and brackish estuaries where freshwater mixed with salt. This tolerance for varying salinity gave them access to ecosystems most marine predators couldn't reach. They could hunt in river systems far inland, dominate coastal shallows during breeding season, and retreat to marine environments when conditions changed. Some researchers believe certain species even ventured briefly onto land, hauling themselves across beaches or mudflats like modern horseshoe crabs. Trackways from the Silurian and Devonian show arthropod footprints matching Eurypterid limb patterns, suggesting these nightmare predators could pursue prey right up to the water's edge. Their sensory systems were sophisticated for the time. Large compound eyes provided wide fields of vision and excellent motion detection. The eyes could track prey from multiple angles simultaneously, giving Eurypterids comprehensive awareness of their surroundings. Their bodies were covered in fine sensory hairs and ridges that detected vibrations in water, allowing them to sense prey movements even in murky conditions or darkness. This combination of visual and vibrational sensing made them devastating ambush predators. They could wait motionless in sediment, with only their eyes exposed, then explode into action when prey wandered within striking range. Their pincers would snap shut, their paddle limbs would propel them forward, and their target would have no chance to escape. Different Eurypterid species specialized in different prey. Smaller species hunted trilobites, worms, and juvenile fish, using speed and agility to chase down quick-moving targets. Medium-sized species tackled anything they could overpower, including other Eurypterids. Cannibalism appears common in fossil assemblages, where multiple Eurypterid species coexisted. The largest species, like Jacalopterus, were apex predators capable of taking virtually any animal in their environment. Their massive pincers could grab struggling prey, while their other limbs manipulated the victim into optimal biting position. They weren't just killers. They were surgical predators capable of dismantling prey with terrifying precision. But Eurypterid dominance couldn't last forever. During the Devonian, jawed fish underwent rapid evolutionary radiation. First came the placoderms, with their crushing bite forces and armoured heads. Then early sharks appeared with flexible cartilage skeletons and superior swimming efficiency. These fish were faster than Eurypterids, capable of cruising longer distances and attacking from angles Eurypterids couldn't defend against. They could also crush or tear through Eurypterid exoskeletons with their powerful jaws. The tables had turned. Arthropods that once preyed on early jawless fish now found themselves hunted by more advanced vertebrates. Environmental changes accelerated Eurypterid decline. As continents shifted, and climates fluctuated, coastlines changed shape, sea levels rose and fell, and freshwater systems became increasingly variable. Eurypterids relied heavily on shallow, calm environments, coastal lagoons, river deltas, protected bays. Disruptions to these habitats fragmented populations and reduced available territory. Many species became isolated in shrinking freshwater systems, where they faced increasing competition from other predators and declining food resources. By the Carboniferous, only smaller freshwater eurypterids remained, and their once great diversity had collapsed to a handful of lineages. The end came during the Permian, when massive volcanic eruptions triggered climate instability, ocean acidification, and the destruction of shallow water habitats. Eurypterids, already weakened by competition and environmental stress, couldn't survive the end Permian mass extinction. They disappeared completely, leaving only horseshoe crabs and arachnids as distant relatives within the Chelicerate group. The 8-foot nightmare predators that ruled rivers and shallow seas for over 200 million years were erased entirely, existing now only as fossils and evolutionary footnotes. Their extinction marked the end of the age when arthropods could compete with vertebrates as apex aquatic predators, a title they would never reclaim. The guillotine-jawed, armoured fish that crush bone. Placoderms represented the armoured giants of the Devonian seas, jawed fish covered in thick, bony plates with sharp jaw blades designed to dominate a world where vertebrate predators were still experimenting with body designs. They appeared in the Silurian, exploded in diversity during the Devonian, then vanished almost overnight during the late Devonian extinction events. Compared to groups like sharks or bony fish that would dominate for hundreds of millions of years, placoderms had a remarkably brief evolutionary run. Yet they left an enormous impact. They were the first vertebrates to perfect functional jaws, the first large predators to control marine environments, and some of the earliest animals to show evidence of live birth. Despite all these innovations, they represent one of evolution's most spectacular failures, an entire group that pioneered vertebrate predation but left no living descendants. Dunkleosteus stands as the most famous placoderm, a giant reaching 30 feet in length with a head covered in thick, interlocking armor plates. Instead of teeth, it possessed two massive jaw blades forming a natural guillotine capable of slicing through bone with terrifying efficiency. Biomechanical studies of its skull reveal bite forces rivaling modern crocodiles, with jaw-closing speeds measured in milliseconds. This combination of crushing power and lightning-fast strikes made Dunkleosteus arguably the most dangerous animal of the Paleozoic. It could bite clean through the armor of other placoderms, shear off chunks of prey, or deliver devastating strikes that caused massive trauma. Its eyes were positioned for binocular vision, allowing accurate depth perception when targeting prey. Its armor protected it from attacks by other predators, creating a nearly invincible killing machine. But Dunkleosteus was just one branch of an incredibly diverse group. Arthrodires, the group containing Dunkleosteus, were open water hunters with jointed neck armor, allowing them to lift their heads, an ability no earlier fish possessed. This neck flexibility lets them open their mouths wider and strike from different angles, increasing hunting versatility. Other placoderms, like the antiarchs, were bottom dwellers with box-shaped heads and bizarre armored forelimbs used for propping themselves up or walking along river bottoms. Some placoderms lived in shallow seas, others in deep water, and still others in freshwater rivers. Their body plans range from flattened ray-like forms to bulky, deep-bodied swimmers. This explosive diversity suggests placoderms were rapidly experimenting with different feeding strategies, swimming styles, and ecological niches during a period when vertebrate evolution remained highly flexible. The jaw innovation that placoderms pioneered changed vertebrate evolution forever. Jaws evolved from modifications of the first gill arches, supporting structures originally used for breathing. Placoderms were the earliest vertebrates to perfect this transformation, developing jaws supported by powerful muscles and reinforced by armor plates. Their jaws could generate tremendous bite forces and operate with precision, giving them unprecedented ability to capture, kill, and process prey. Without placoderm jaws, later vertebrates, including sharks, bony fish, amphibians, reptiles, birds, mammals, and humans, would never have developed the complex feeding structures they rely on. Placoderms introduced a revolution in how animals could interact with their environment, transforming passive filter feeders into active hunters. Placoderms also pioneered reproductive innovations. Fossils of species like Matopechis attenboroughii contain embryos preserved with umbilical attachments inside the mother's body, proving that live birth existed hundreds of millions of years before sharks or mammals adopted similar strategies. These fossils show developing embryos connected to their mothers through cord-like structures, receiving nutrients directly rather than developing inside eggs. This means placoderms weren't just experimenting with armor and jaws, they were revolutionizing reproduction in ways that foreshadowed later vertebrate evolution. Their internal anatomy reveals a complexity that contrasts sharply with their heavily armored exteriors, suggesting these were sophisticated animals despite their archaic appearance. Yet despite these innovations, placoderms faced mounting challenges during the late Devonian. New groups of fish evolved with significant advantages. Early sharks developed cartilage skeletons that were lighter and more flexible than placoderm armor, giving them superior speed and maneuverability. Ray-finned fish evolved lightweight scales and versatile fin designs that allowed rapid turns and efficient swimming. As marine ecosystems grew more complex, mobility became more important than raw defensive power. Placoderms were formidable but inefficient. Their heavy armor restricted rapid movement and long-distance swimming. In races and chases, they increasingly found themselves outmatched by faster, more agile competitors. Environmental catastrophes delivered the final blows. The late Devonian experienced repeated ocean anoxia events, periods when massive stretches of ocean lost dissolved oxygen. These anoxic zones killed fish by suffocation and disrupted entire food webs. Placoderms, depending on stable shallow habitats, were hit hardest. Reef systems collapsed, coastal waters became inhospitable, and nutrient cycles changed dramatically as land plants spread across continents. Placoderms that once filled every available niche suddenly found themselves squeezed by environmental stress and biological competition simultaneously. The late Devonian extinction eliminated placoderms entirely. Not a single lineage survived into the Carboniferous. Sharks and bony fish, their primary competitors, survived, diversified, and eventually conquered every aquatic environment on Earth. Placoderms, despite being evolutionary pioneers that introduced jaws and sophisticated predatory behaviors to vertebrates, became a dead-end branch. Their armor proved ultimately inferior to the flexible, lightweight designs of their successors. Their jaw structures, while powerful, lacked the versatility of shark jaws or the precision of bony fish mouths. Evolution moved past them, and their entire group disappeared as if it had never existed. The armored giants that terrorized Devonian seas left behind only fossils, warnings that even the most fearsome predators can vanish when the world changes faster than they can adapt. The saber-toothed proto-mammals that ruled before dinosaurs. Gorgonopsians were the apex predators of the late Permian world, and they looked like nightmares carved from muscle and teeth. These weren't reptiles or mammals, but something in between. Early synapsids related to the evolutionary line that would eventually produce mammals, yet fundamentally different in form and function. With elongated saber teeth, forward-facing eyes, and bodies built for pursuit across harsh floodplains, Gorgonopsians represented the pinnacle of pre-dinosaur predatory evolution. They dominated terrestrial ecosystems for millions of years before the Permian-Triassic extinction, the worst mass extinction in Earth's history, erased them completely. Their rise and fall demonstrates evolution's ability to produce sophisticated killing machines, and the brutal reality that even perfect predators can be wiped out overnight. The iconic image of a Gorgonopsian comes from In Nostrum Surveyor, a 2-meter predator with massive slicing canine teeth and a skull designed for delivering deep, penetrating bites. These weren't short stabbing teeth like those of most reptilian predators. They were true sabers, elongated and laterally flattened blades used for precision killing. But the group showed tremendous diversity. Some species were fox-sized, quick and agile hunters of small prey. Others approached tiger size, capable of taking down the largest herbivores of their time. All shared key features: those distinctive saber teeth, lightly built limbs suggesting fast movement, and skulls shaped to deliver powerful, controlled bites, rather than simple, crushing force. Their skulls were engineering masterpieces. Gorgonopsian jaw joints allowed gaps approaching 90 degrees, far wider than modern big cats. This extreme opening was necessary to deploy their sabers effectively without the teeth catching on the lower jaw. They would approach prey, open their jaws to maximum gape, then drive the saber teeth downward into vital areas: throats, necks, major blood vessels. Bite marks preserved in fossil bones show they targeted soft tissues with surgical precision, much like later saber-toothed cats would millions of years in the future. This convergent evolution, saber teeth appearing independently in completely unrelated predatory groups, demonstrates that certain killing strategies are so effective that evolution returns to them repeatedly across different eras. Unlike earlier amphibian-like predators that sprawled with legs out to the sides, Gorgonopsians held their limbs directly beneath their bodies in an upright posture. This structural change had profound implications. It allowed sustained running rather than the slow waddle of sprawling animals. It reduced energy expenditure during movement. It enabled better balance and maneuverability during chases or when making kills. Fossil trackways show Gorgonopsians moved with a steady, efficient gait, suggesting they could cover long distances while hunting. In the harsh late Permian landscape, where prey and water sources were widely scattered, this endurance would have been crucial for survival. Evidence suggests Gorgonopsians may have been warm-blooded or at least had elevated metabolisms compared to reptiles. Their skulls show enlarged attachment areas for jaw muscles, indicating not just strong bites, but fast ones. The rapid muscle contractions needed for quick strikes require high metabolic rates. Their eyes faced forward rather than to the sides, improving depth perception essential for active hunting. Some fossils show facial bone patterns suggesting whisker-like sensory structures, similar to those in mammals. Their rib structures indicate more flexible breathing systems than typical reptiles, possibly allowing the sustained oxygen delivery needed for active lifestyles. While they weren't true mammals, they were moving in that direction, testing metabolic and physiological features that mammals would later perfect. The late Permian environment demanded these adaptations. The supercontinent Pangaea created extreme climates with scorching summers, prolonged droughts, and unpredictable rainfall. Floodplains alternated between lush vegetation and barren wastelands. Herbivores like dicynodonts and precursors roamed these landscapes, forming the prey base Gorgonopsians depended on. Many prey species had developed armor-like bony plates or thick hides for protection, so Gorgonopsians couldn't rely on brute force crushing. Instead, they evolved precision weapons, those saber teeth that could slip between armor plates or pierce through tough skin to reach arteries and windpipes beneath. But specialization created vulnerabilities. Saber teeth were devastating weapons, but also fragile. If a canine broke during a struggle, that Gorgonopsians' hunting effectiveness dropped dramatically. Their lightly built bodies made them excellent pursuit predators, but poorly suited for grappling with heavily armored herbivores. Their dominance lasted only as long as ecosystems remained stable enough to support populations of large, active predators requiring substantial prey biomass to survive. The end Permian mass extinction shattered that stability. Massive volcanic eruptions in Siberia released greenhouse gases triggering runaway global warming. Acid rain poisoned terrestrial ecosystems, Oceans lost oxygen and released toxic hydrogen sulfide. Food webs collapsed from the bottom up. Plants died first, then herbivores, and finally the predators that depended on them. Gorgonopsians, positioned at the top of food chains, were among the first large terrestrial animals to go extinct completely. Their highly specialized predatory lifestyle left them no flexibility when prey disappeared. They couldn't switch to scavenging or supplement their diets. They were built for killing large prey, and when that prey vanished, so did they. No Gorgonopsians survived into the Triassic period. Their extinction opened ecological space for new predators, the rhapsids, like cynodonts, that would eventually give rise to true mammals, and later the archosaurs that would become dinosaurs. But none of these successor groups ever recreated the exact form of Gorgonopsians. Their particular combination of saber teeth, upright posture, and forward-facing eyes was unique to the late Permian. They represented evolution's first serious attempt at creating mammal-like predators, an experiment that succeeded brilliantly for millions of years before being completely erased. The animals that eventually inherited Earth, dinosaurs, then mammals, would use different designs, different strategies, and different body plans. Gorgonopsians remain frozen in deep time, apex predators that ruled their world completely, then vanished as if they had never existed. The armoured river tanks with mechanical walking arms. Antiarchs were among the strangest fish that ever existed, heavily armoured bottom feeders that looked like someone had crossed a turtle with a tank and added mechanical arms. These were plesioderms, relatives of the fearsome Dunkleosteus, but they evolved in completely opposite directions. Instead of becoming apex predators, antiarchs became specialised bottom dwellers with bizarre appendages that function more like articulated limbs than fins. They spread worldwide during the Devonian, inhabiting rivers, lakes and shallow seas with remarkable success for tens of millions of years. Then the late Devonian extinction eliminated them entirely. Their strange design represents one of evolution's boldest experiments in fish locomotion, an attempt to give fish limb-like structures millions of years before tetrapods evolved actual legs. Bothriolopus, the best-known antiarch, was roughly the size of a loaf of bread, though some species grew larger. Its body is divided into two distinct regions, a heavily armoured front section and a soft, flexible tail. The armoured portion consisted of thick bone plates arranged like interlocking puzzle pieces, giving antiarchs their characteristic boxy appearance. These plates weren't just for protection, they served as structural support in environments with strong currents or shifting sediments where soft-bodied fish would be tumbled helplessly. The weight of the armour also kept antiarchs pressed firmly against the bottom, preventing them from being swept away during floods. But the most iconic feature was their pectoral appendages, elongated, jointed structures extending from the sides of their armoured box. These weren't fins in any conventional sense. They were stiff, bony arms that could bend at distinct joints, resembling elbows and wrists. Fossils show wear marks on the undersides of these appendages, proving antiarchs used them for locomotion. They would prop themselves up on these arms, steer through muddy bottoms, or walk across riverbeds using coordinated movements. High-resolution CT scans reveal intricate joint surfaces inside the appendages, showing they were capable of controlled, deliberate movements rather than simple flexing. This represents a major evolutionary experiment in limb development, occurring millions of years before vertebrates colonized land. Their feeding strategies were equally specialized. Antiarchs had small mouths located on the underside of their armored heads, positioned perfectly for bottom feeding. They likely sucked up detritus, algae, and small organisms hidden in sediment, filtering food from mouthfuls of mud. Their jaws were simple compared to predatory placoderms. No crushing plates or slicing blades, just basic structures adequate for processing soft food. Their eyes sat near the top of their heads, oriented upward to watch for predators while they fed. This eye placement resembles modern bottom-dwelling fish like sturgeons, rays and flounder, all of which need to monitor threats from above while their mouths work below. Antiarchs achieved remarkable geographic distribution. Fossils have been found on every continent, including Antarctica, showing they could adapt to diverse environments from tropical rivers to temperate coastlines. During the Devonian, when predators like Eurypterids and early sharks prowled aquatic ecosystems, Antiarch armour provided crucial protection, but that same armour made them slow and cumbersome. They couldn't flee quickly when threatened. They had to rely entirely on their defensive plating. This strategy worked well in calm, protected environments, but became a liability in dynamic, rapidly changing ecosystems. Recent three-dimensional reconstructions of Antiarch anatomy reveal surprising complexity. Their pectoral appendages had muscles, ligaments, and specialized joint surfaces that allowed sophisticated movements. They could rotate their arms, adjust angles, and coordinate both sides for efficient locomotion. This level of limb functionality shows vertebrates were experimenting with appendage control long before tetrapods evolved. Although these structures never led directly to legs, Antiarchs were a side branch that died out. They demonstrate evolution exploring multiple solutions to the problem of movement. If Antiarchs had survived, perhaps fish with true walking appendages would have evolved from them rather than from lobe-finned fish. Instead, the Antiarch experiment ended completely. Competition drove their decline. During the Devonian, ray-finned fish and lobe-finned fish underwent rapid diversification. These fish had more flexible fins, more efficient swimming capabilities, and more sophisticated feeding structures. As rivers and lakes filled with faster, more agile competitors, Antiarchs found themselves outpaced in the struggle for food and territory. Their armour, once an advantage, became a burden when speed and flexibility mattered more than defence. Young Antiarchs would have been particularly vulnerable. Their armour wouldn't develop fully until maturity, leaving juveniles exposed to predation in increasingly dangerous waters. Environmental changes delivered the killing blow. The late Devonian saw dramatic shifts in water temperature, oxygen levels, and sediment flow as land plants spread globally and altered nutrient cycles. Many shallow water habitats, the calm rivers, protected lakes, and coastal shallows where Antiarchs thrived, became unstable or disappeared entirely. When late Devonian extinction events triggered widespread anoxia in aquatic systems, fish dependent on stable, oxygen-rich environments died en masse. Antiarchs, already weakened by competition and habitat loss, couldn't recover. By the Carboniferous, they were gone completely. The walking armoured fish that had colonised rivers and lakes across ancient continents left no descendants. Their mechanical arm fins represent an evolutionary path not taken, a glimpse of what might have been if fish had evolved limbs through a different mechanism. Instead, tetrapod limbs evolved from lobe-finned fish with completely different fin structures. Antiarchs remain evolutionary oddities, fish that almost had arms, that almost learned to walk, but ultimately vanished before perfecting either innovation. The boomerang-headed amphibians of ancient swamps. Diplocaulus possessed one of the most bizarre skulls in evolutionary history, a wide, triangular head shaped like a boomerang with two long horn-like projections extending outward. This wasn't a slight evolutionary quirk, but a radical body modification that has puzzled paleontologists for over a century. Diplocaulus belonged to the lepospondals, a diverse group of early tetrapods that experimented with wildly different body forms during the Carboniferous and Permian periods. While some lepospondals resembled salamanders and others looked like limbless snakes, Diplocaulus went a completely different direction, evolving a head so extreme it seems pulled from science fiction rather than Earth's fossil record. The boomerang skull wasn't decorative, it served a hydrodynamic function. Recent biomechanical studies suggest this bizarre shape acted as a hydrofoil, generating lift as the animal swam. Water flowing over and under the skull's surfaces would create pressure differences that kept Diplocaulus level in the water column. This meant Diplocaulus could glide through water with minimal effort, maintaining stable depth without constant swimming. The design also provided excellent maneuverability. By angling its head, Diplocaulus could adjust its position quickly, darting upward to snatch prey from above, or diving downward to escape threats. Modern submarines use similar principles with horizontal stabilizers, but Diplocaulus evolved this solution hundreds of millions of years ago using only skull bones. The skull's shape also had defensive implications. That wide boomerang profile made Diplocaulus extremely difficult to swallow. Most aquatic predators of the time, large amphibians, early reptiles and various fish, needed to engulf prey headfirst to swallow it. Diplocaulus's head was simply too wide to fit in most predators' mouths. Even if a predator managed to grab Diplocaulus, the horn-like projections would catch on the predator's jaws, making it impossible to work the prey down into the throat. This passive defense let Diplocaulus survive in environments filled with hungry predators without needing speed, armor, or active fighting abilities. Other lipospondylls explored completely different survival strategies. Istopoda evolved into long, limbless forms resembling eels or oversized earthworms. They had no legs whatsoever, moving instead through serpentine undulation. This body plan lets them squeeze through tight spaces in dense vegetation or burrow into soft mud, hunting small prey that larger predators couldn't reach. Nectroidea, another lipospondyl group, had flattened bodies and paddle-shaped tails for swimming, resembling aquatic salamanders. Still others were stubby-bodied with reduced limbs, built for life on muddy stream banks. This diversity shows lipospondylls weren't a single type of animal, but a whole cluster of evolutionary experiments branching off from early tetrapods, each testing different solutions to survival challenges. Their skeletal structure set them apart from other early tetrapods. Lepospondyl vertebrae formed from single pieces of bone called lepospondyl centra, rather than the multiple fused elements typical of amphibians and amniotes. This gave their spines extra stiffness and simplicity, which may have been advantageous for small-bodied animals that didn't need the flexibility of larger tetrapods. Their skulls were also more lightly built than those of temnospondyl amphibians, suggesting they relied more on agility and specialized adaptations than on brute strength or heavy construction. Despite their innovations, lepospondylls never achieved large sizes. Most species stayed under a foot long, and even the largest rarely exceeded a meter. This size restriction made them vulnerable to the growing number of larger predators evolving during the Carboniferous and Permian. Early reptiles, large temnospondyl amphibians, and eventually gorgonopsians all saw small lipospondylls as convenient prey. The rapid evolution of these terrestrial predators may have squeezed lepospondylls into increasingly narrow ecological niches, where their specialized body forms provided just enough advantage to survive. Lepospondylls thrived in the warm, swampy environments of the Carboniferous, when wetlands covered vast areas and freshwater habitats remained stable. But as the Permian progressed, global climates shifted toward drier, more seasonal conditions. Wetlands shrank dramatically. River systems became less predictable. Freshwater habitats fluctuated wildly between floods and droughts. Lepospondylls, many specialized for aquatic or semi-aquatic lifestyles, struggled in these unstable landscapes. Their delicate bodies and swimming-focused adaptations became disadvantages as environments grew harsher and less predictable. Competition from early amniotes accelerated their decline. Reptiles and early mammal ancestors evolved waterproof skin, more efficient lungs, and eggs that could be laid on land away from water. These adaptations let amniotes colonize dry habitats completely inaccessible to lepospondylls. As amniotes diversified into insect eaters, herbivores, and predators, they occupied ecological roles lepospondylls might otherwise have filled. Lepospondylls found themselves confined to shrinking wetland refuges, competing for diminishing resources while better adapted animals spread across the changing landscape. By the end of the Permian, lepospondylls had largely disappeared. The Permian-Triassic extinction finished off the remaining lineages. Their diverse experiments in body form, boomerang heads, limbless bodies, paddle tails, and countless other variations, all ended in evolutionary dead ends. No modern tetrapod descended from lipospondylus. They represent a separate exploration of what tetrapods could become, an alternative pathway that flourished briefly before being outcompeted and eliminated. Diplocaulus and its relatives remain evolutionary curiosities. Amphibians that tried radically different designs during a critical period in tetrapod evolution succeeded for millions of years, then vanished completely when the world changed around them. The diamond-scaled forest giants that built our coal. The late Carboniferous forests looked nothing like modern woodlands. Towering above ancient swamps stood giant lycopsid trees like lepidodendron, covered not in bark, but in diamond-shaped scale patterns. These weren't trees in the botanical sense. They didn't grow wood rings or branches the way modern trees do. Instead, they constructed tall, hollow trunks from soft tissues, shooting upward with reckless speed to compete for sunlight in the dense, humid swamps. For millions of years, these bizarre trees dominated terrestrial ecosystems, fundamentally altering global climate and laying down the massive coal deposits we still mine today. Yet despite their overwhelming success, they represented an evolutionary dead end, a design perfectly suited to one specific environment that collapsed completely when conditions changed. A mature lepidodendron could reach heights of 30 to 40 metres, rivaling modern redwoods, but its internal structure was radically different. Modern trees grow thick wood through secondary growth, adding rings year after year. Lycopsids did nothing of the sort. Their trunks were hollow in the centre, filled with soft, spongy tissues instead of solid wood. They grew at breathtaking speed, but remained structurally fragile. They depended entirely on the constant support of waterlogged swamp soils, where their roots could spread in wide, shallow networks. Those roots weren't true roots at all, but modified underground stems called stigmarian systems, covered in rootlets that absorbed nutrients from oxygen-poor mud. These networks formed massive tangles that stabilized the trees in soft sediment, but couldn't function in drier soils. Lycopside leaves sprouted directly from the trunk as long, narrow structures that dropped off as the tree matured. Each fallen leaf left behind a distinctive diamond-shaped scar on the trunk, the fossil signature that makes lycopsids instantly recognizable. Near the top, the trunk finally branched into a crown-like cluster where the tree concentrated its photosynthetic leaves. From these crowns grew enormous spore cones, some larger than a human arm, packed with millions of spores. Lycopsides reproduced through these spores rather than seeds, which tied them irrevocably to humid environments where spores could disperse successfully through water or saturated air. The growth pattern of lycopsids was unlike any modern tree. Fossil evidence suggests these giants lived only 10 to 15 years, incredibly brief for organisms of such size. They grew explosively fast, reaching full height in just a few years, then reproduced once in a massive spore release before dying. This rapid life cycle made them perfectly adapted to the unstable coal swamps, where floods and sedimentation created constantly changing conditions. Fast growth let lycopsids colonize disturbed areas before competitors arrived. Brief lifespans meant they didn't need to invest in long-term structural support, like wood. They were the weeds of the Carboniferous, fast-growing opportunists that could dominate newly created habitats in years rather than decades. This specialization was simultaneously their greatest strength and fatal weakness. Lycopside forests altered Earth's atmosphere by pulling massive amounts of carbon dioxide from the air through photosynthesis. When the trees died and fell into oxygen-poor swamp waters, they didn't decay normally. Instead, they were buried in sediment where they slowly compressed into coal over millions of years. The coal seams that powered the Industrial Revolution and still provide energy today are the compressed remains of these bizarre forests. Lycopsids literally reshaped Earth's climate and geology, but they could only do so in one specific environment: waterlogged swamps with stable water levels. As the Carboniferous ended, conditions began changing. The supercontinent Pangaea was forming, creating larger land masses with extensive interior regions far from oceans. Rainfall patterns shifted. Seasonal climates appeared where year-round wetness had prevailed. Coal swamps began drying out, and lycopsids, entirely dependent on saturated soils and spore-based reproduction, had no way to adapt. Their whole life cycle required stable wetlands. Without constant water, their shallow stigmarian roots couldn't support the tall trunks. Without humidity, their spores died before establishing new trees. Without swamps, their entire ecosystem collapsed. Meanwhile, seed plants, early gymnosperms, were rising to dominance. Seed plants could survive in dry environments that killed lycopsids. Their seeds protected embryos inside resistant coatings and could remain dormant through droughts or unfavourable seasons. They developed true wood with secondary growth, allowing stronger trunks that didn't need swamp support. They grew deeper roots that could access water in drier soils. These advantages let gymnosperms colonize upland areas, hillsides, and seasonally dry regions that lycopsids could never tolerate. As global climates dried and forests diversified, gymnosperms pushed lycopsids into the shrinking wetland remnants that remained. The final blow came as swamp environments became patchy and unpredictable. Lycopsids needed vast, continuous wetlands for successful spore dispersal. Fragmented habitats meant spores couldn't reach suitable germination sites. Without stable wetland systems, juvenile lycopsids couldn't establish themselves before droughts killed them. Their towering, fast-growth strategy, which had made them unbeatable in stable swamps, became a fatal flaw in changing environments. By the early Permian, the giant lycopside forests had vanished completely from Earth. Small lycopside species survived as understory plants and still exist today as tiny club mosses. But the towering forest giants were gone forever. Their legacy persists in the most literal way possible, as fossil fuel beneath our feet. The coal we burn for electricity, the carbon we've released into the atmosphere since the Industrial Revolution, the climate change we're experiencing now, all trace back to those bizarre Carboniferous forests. Lycopsids stored solar energy 300 million years ago, transforming it into compressed carbon that humans would eventually extract and burn. We're releasing in centuries the carbon that took millions of years to sequester. The giant lycopside trees that built our coal supply represent one of evolution's most successful dead ends. Organisms that dominated Earth so completely they changed its chemistry, yet couldn't adapt when the world moved on. The spiked walking nightmares that defied classification. Before arthropods perfected their body plans, evolution produced creatures so strange that scientists spent over a century arguing about what they even were. Hallucigenia stood at the center of this confusion, a Cambrian animal initially reconstructed completely backwards and upside down, creating an image so bizarre it earned a name meaning hallucination. When paleontologists first studied it in the 1970s, they placed its spines downward as walking stilts and its soft legs upward as feeding tentacles, producing a reconstruction that looked like a floating nightmare rather than a real animal. Only in the 1990s did scientists flip it right side up. Then, in 2015, high-resolution microscopy finally revealed its head, solving one of paleontology's strangest puzzles and confirming hallucigenia was even weirder than anyone imagined. Hallucigenia belonged to lobopodians, worm-like animals with stubby, unjointed legs that crawled across Cambrian seafloors over 500 million years ago. These creatures represented evolutionary experiments in body design that occurred before arthropods locked in their successful formula of jointed legs and segmented exoskeletons. Lobopodians combined features from modern velvet worms, hints of future arthropod traits, and entirely unique characteristics that never appeared again. The result was a menagerie of creatures that looked like they belonged in fever dreams: walking worms covered in spines, tube bodies sprouting multiple feeding arms, and organisms so alien that placing them in evolutionary trees remains contentious. Hallucigenia's body consisted of a narrow tube with multiple pairs of soft lobopod legs underneath and rigid spines projecting from its back. The spines weren't random. They formed paired rows arranged symmetrically, creating a porcupine-like defensive profile. Each spine was stiff and sharp, likely composed of hardened proteins or early forms of cuticle. The 2015 microscopy study that finally identified Hallucigenia's head revealed a bulbous front end with a simple mouth ringed by tiny teeth or denticles. This mouth was designed for scraping or grasping soft food from surfaces, not for hunting or crushing. Hallucigenia was a grazer, slowly moving across microbial mats and feeding on organic material. What makes lobopodians fascinating is their role as transitional forms. They possess features that would later become essential to arthropod success, but in primitive, experimental versions. Take Microdictyon, another lobopodian known for its distinctive net-like armor plates. These plates sat along the sides of its body like small shields, not quite the segmented exoskeleton of arthropods, but clearly moving in that direction. Collincium, sometimes called the walking cactus, pushed defensive spines to the extreme with its entire body covered in spectacular projections, while long, delicate feeding appendages extended from its head like sensory antennae. Each species represented a different approach to the same problems: how to move, how to feed, how to defend against the emerging predators filling Cambrian seas. Recent discoveries from China's Zhenjiang fossil beds reveal lobopodian diversity far exceeding earlier estimates. Some species had multiple sets of feeding arms capable of manipulating food while walking. Others developed elaborate mouth structures with rings of teeth arranged in spiral patterns, nightmare fuel predating sharks' similar designs by hundreds of millions of years. Some had eye stalks protruding from their heads like periscopes, giving them elevated viewpoints while their bodies remained hidden. This anatomical diversity shows evolution was throwing dozens of designs at early animal life, testing countless variations to see what worked. One crucial discovery involves claw-like structures at the ends of lobopodian legs. Microscopic analysis reveals these claws consist of stacked proteins remarkably similar to the materials in modern arthropod claws and insect cuticle. This suggests arthropod features didn't appear suddenly, but evolved gradually from simpler precursors. Lobopodians were in the testing phase, developing proto-claws that could grip and anchor, but lacked the sophistication of true arthropod appendages. Their legs could hold onto rocks, secure prey, and provide traction, but couldn't manipulate objects with the precision later arthropods achieved. The spines covering many lobopodians served vital defensive purposes. The Cambrian explosion had produced radiodonts and other predators developing increasingly efficient killing strategies. Soft-bodied animals became easy targets. Lobopodians responded with external defenses, spines that made them difficult to grab or swallow, armor plates that protected vital organs, and body shapes that discouraged attacks. Hallucigenia's paired spine rows created a profile that would cause pain to any predator attempting to bite down. Collincium's dense spine coverage turned it into a mobile pincushion. These weren't perfect defenses, but in a world where predators were still refining their hunting techniques, passive protection bought crucial survival time. Yet even with these adaptations, lobopodians couldn't compete long-term with true arthropods. By the late Cambrian and early Ordovician, arthropods had evolved segmented bodies, hardened exoskeletons, and fully jointed limbs. These improvements provided superior mobility, better protection, and greater adaptability. Lobopodians, with their soft bodies, simple legs, and limited flexibility, were outcompeted in nearly every environment. Most lineages disappeared completely. Only a handful of descendants survived in obscure niches: modern velvet worms living in tropical forests under rotting logs, and tardigrades, microscopic water bears that can survive extreme conditions but bear little resemblance to their ancient ancestors. Hallucigenia and its armoured relatives represent evolution at its most creative and experimental. They weren't failures or mistakes. They were prototypes testing fundamental innovations. Their experiments with protection, locomotion, and feeding strategies laid groundwork for the dominant arthropods that would later inherit Earth. But in evolution's brutal calculus, being a prototype means being replaced by refined versions. The walking nightmare cacti that crawled through Cambrian seas were stepping stones toward arthropod success, not the final destination. They thrived for millions of years, pioneered crucial innovations, then vanished completely when better designs emerged. Their fossils remain as monuments to evolution's willingness to experiment wildly and to discard even successful experiments when superior alternatives appear. The spiral-plated sea creatures that broke every rule. Helicoplacoids represent one of evolution's briefest and strangest experiments. Marine animals with spiraling body plates that appeared suddenly in the early Cambrian, thrived briefly, then vanished completely within a few million years. Their fossils baffled scientists for decades because they didn't fit any known animal pattern. Modern echinoderms, starfish, sea urchins, sea cucumbers follow strict 5-part radial symmetry. Helicoplacoids ignored this rule entirely, building their bodies around helical spirals that twisted like animated seashells made of interlocking armour. For years, paleontologists couldn't determine what group they belonged to. Only when researchers examined how their plates grew and compared microscopic structures with other early echinoderms did the connection become clear. Helicoplacoids were echinoderms, just incredibly weird ones that tried a radically different approach to body design. The spiral structure wasn't merely decorative, it was functional. Helicoplacoid plates were arranged in rotating rows that spiraled around the body from bottom to top, creating a twisting pattern. These plates could expand and contract as the animal moved or fed, flexing in ways no living echinoderm can replicate. The arrangement worked almost like an accordion made of stone, allowing the body to subtly twist or bulge. This flexibility suggests helicoplacoids were adapted to shifting environments, perhaps soft seafloors where rigid bodies would sink, or areas with strong currents where flexibility helped maintain position. Their mouths sat near the top of the body, and the spiral plating likely helped channel water and food toward this opening. Scientists believe helicoplacoids fed on suspended particles or organic debris drifting through early Cambrian seas. Some researchers argue they rotated slowly while feeding, using their spiral grooves to create water currents that directed nutrients toward the mouth, a living vortex trap. Others suggest they simply lay on the seafloor, oriented with mouths upward, letting natural currents bring food to them passively. Either strategy would explain why they evolved such unusual body shapes. The spiral design optimized water flow in ways that standard echinoderm symmetry couldn't match. Fossil locations provide crucial clues about helicoplacoid ecology. Their remains appear almost exclusively in rocks formed from rapidly shifting, storm-disturbed environments, especially in what is now Western North America. These were unstable habitats with constantly moving sands and frequent sediment avalanches. Helicoplacoids may have specialized for living in this kind of dynamic setting where their flexible, spiraling bodies help them anchor or adjust to changing currents. While other early echinoderms colonized stable reef environments or calm seafloors, helicoplacoids carved out a niche in the chaotic zones other animals avoided. But specialization came with severe costs. As Cambrian seas evolved and ecosystems matured, those unstable, storm-dominated habitats became less common. Seafloors stabilized, burrowing animals appeared, churning through sediments and fundamentally changing ocean bottom environments. Reef systems expanded. These changes eliminated the specific conditions helicoplacoids depended on. When the seafloor began churning under the activity of worms and arthropods, the delicate balance that allowed helicoplacoids to thrive collapsed. They couldn't adapt to stable environments where standard echinoderm body plans worked better. They couldn't compete in complex habitats where mobility and feeding versatility mattered more than specialized spiral designs. Identifying helicoplacoids as echinoderms took decades of scientific detective work. Their bizarre symmetry didn't match the 5-part pattern paleontologists expected from the echinoderm family. Early researchers suggested they might be mollusks, worms, or something entirely separate. Only detailed examination of their plate microstructure revealed the truth. The calcite plates in helicoplacoid fossils showed distinctive patterns, the stereome structure characteristic of echinoderm skeletons. This microscopic architecture forms through specific biological processes unique to echinoderms. Once scientists recognized this signature, helicoplacoid classification became clear. They were early members of the echinoderm family tree that branched off before 5-part symmetry became fixed, testing an alternative body plan that ultimately failed. Their rapid extinction demonstrates a crucial evolutionary principle. Even perfectly adapted organisms can vanish if their environment disappears. Helicoplacoids weren't outcompeted by superior predators or better designed relatives. They simply lost the specific habitat conditions they required. Evolution optimized them for storm-disturbed, shifting environments that became rare as the Cambrian progressed. When those habitats vanished, helicoplacoids had nowhere to go. Their specialized bodies couldn't function in stable settings. Their feeding strategies didn't work in calm waters. Their entire existence depended on environmental chaos that eventually gave way to order. Other echinoderms survived by maintaining flexible body plans that could adapt to changing conditions. They evolved mobile arms, protective spines, and varied feeding strategies. They colonized reefs, sandy bottoms, deep waters, and shallow tides. This versatility carried them through multiple mass extinctions, climate changes, and ecological upheavals. Helicoplacoids achieved none of this flexibility. They lived for perhaps 3 to 5 million years, an evolutionary blink, before disappearing forever. Their spiral-plated bodies represent evolution testing a radical idea that worked brilliantly in one narrow context, but couldn't scale beyond those initial conditions. They remind us that successful designs aren't always general-purpose solutions. Sometimes evolution creates perfect specialists that thrive magnificently in specific niches, then vanish instantly when those niches cease to exist. The asymmetrical armoured anomalies that defied echinoderm logic. Stylophorans ranked among the most unpredictable animals in the echinoderm family, creatures so bizarre that scientists spent decades unable to agree on what they were or where they belonged. They lived throughout the early Paleozoic, disappearing long before dinosaurs appeared, and they broke almost every rule associated with their relatives. Modern echinoderms follow 5-part radial symmetry. If you know starfish, sea urchins, or sea lilies, you know this fundamental pattern. Stylophorans didn't care. Their bodies were asymmetrical, covered in armor plates, and built around a single, long appendage that experts still debate. For years, some researchers believed stylophorans were missing links between echinoderms and chordates. the group containing vertebrates. Others argued they were failed echinoderm experiments. Today, most paleontologists agree stylophorans were echinoderms, just ones that broke so many evolutionary rules they could never achieve long-term survival. A typical stylophoran had two main components. First was a flattened, asymmetrical body called a theca, covered in interlocking calcite plates functioning as armour. This body showed no obvious front or back, no clear top or bottom, just an irregular, shield-like structure. Attached to this theca was the olacophore, a long appendage built from calcite elements arranged like a flexible rod. This structure became the centre of scientific controversy. Early researchers thought it was a proto-spine, making stylophorans early vertebrate relatives. This interpretation came from superficial resemblance to a notochord, the primitive backbone precursor found in early chordates. Others countered that the olacophore functioned like a feeding arm, sweeping particles toward the mouth, similar to structures in some living echinoderms. Modern imaging techniques finally settled the debate. High-resolution microscopy and CT scanning revealed the olacophore's internal structure matched echinoderm tissue patterns, not vertebrate ones. The calcite elements showed the stereom microstructure characteristic of echinoderm skeletons, a distinctive porous architecture that forms through specific biological processes unique to this group. The olacophore wasn't a backbone precursor. It was echinoderm tissue engineered into a unique tool, probably used for feeding, positioning, or sensory functions. This discovery confirmed stylophorans as legitimate echinoderms, just extraordinarily unusual ones. But confirming their family connections didn't make them less strange. Their asymmetry remains baffling. Echinoderms typically develop radial symmetry early in their development, with larvae that initially look bilaterally symmetric transforming into radially symmetric adults. Stylophorans never followed this pattern. They remained asymmetric throughout their lives, suggesting they branched off before five-part symmetry became developmentally fixed in the echinoderm lineage. This means stylophorans preserved an ancient body plan that other echinoderms abandoned. Alternatively, their asymmetry might have been an adaptation for specific lifestyles, perhaps bottom-dwelling or sediment-clinging habits, where symmetry provided no advantage. The variety within stylophorans suggests they were trying numerous survival strategies simultaneously. Some species show evidence of deposit feeding, using their olacophoras to sweep food toward mouths on the theca. Others may have stood partly upright, positioning their appendages to capture suspended particles from water currents. A few fossils suggest individuals could attach temporarily to hard surfaces, anchoring themselves before moving elsewhere. This behavioural diversity hints that stylophorans weren't locked into single lifestyles, but instead experimented with different approaches, none of which proved successful enough to persist beyond the Ordovician. Their extinction likely resulted from multiple pressures. The Ordovician saw rapid evolution in marine predators. Early cephalopods developed shells and tentacles, becoming formidable hunters. Jawless fish, though still primitive, grew larger and more numerous. These predators could crush or pierce the armor plates that protected earlier animals. Stylophorans, with their awkward shapes and limited mobility, may have been easy targets. They couldn't swim quickly to escape. Their armor, while protective, wasn't as comprehensive as shells or complete exoskeletons. Predators, learning to flip them over or attack unarmored sections, could kill them efficiently. At the same time, other echinoderms evolved more practical designs. Starfish developed flexible arms that could pry open shells and access protected prey. Sea lilies created filter-feeding crowns that efficiently strained plankton from passing currents. Sea urchins grew protective spines and developed the ability to burrow into sediments for safety. These innovations provided clear advantages: better feeding efficiency, improved defense, greater mobility. Stylophorans couldn't match these improvements. Their asymmetric bodies and mysterious aula weren't bad designs, but they weren't competitive with the refined alternatives appearing in other echinoderm lineages. Changes in ocean chemistry may have added final pressure. As reef systems expanded during the Ordovician and seafloors became more oxygenated, ecosystems shifted toward more active, mobile lifestyles. Organisms relying on slow feeding methods or stationary positions faced increasing disadvantages. Stylophorans were likely too specialized in their unusual body forms to adapt quickly. Their asymmetry, once an experimental body plan exploring alternatives to radial symmetry, became a liability when successful competitors appeared. By the end of the Ordovician, Stylophorans had vanished completely. They represent evolution testing alternatives to the dominant echinoderm blueprint. For millions of years, they proved this alternative could work. They spread globally, diversified into multiple species, and occupied various ecological roles. But in the long game of evolution, simply working isn't enough. Designs must be competitive, adaptable, and robust against environmental changes. Stylophorans were none of these things. They were curiosities, successful enough to persist for millions of years, but never refined enough to compete with mainstream echinoderm designs. Their extinction reminds us that evolution doesn't preserve all successful experiments, only those that remain competitive when circumstances change. The filter-feeding colonial ribbons that dominated then vanished. Graptolites dominated Paleozoic oceans as some of the most abundant and successful animals of their era. Yet they're also among evolution's strangest experiments. Colonies of tiny zooids living together in structures that resembled saw blades, tuning forks, or intricate calligraphy carved into stone. For over 100 million years, they drifted through ancient seas as efficient filter feeders, spreading so widely they became some of the most useful index fossils for dating Paleozoic rocks. Eventually, they went extinct almost completely, leaving only a tiny group of survivors that evolved into modern pterobranchs, obscure animals most people have never heard of. Their story demonstrates how even hugely successful, globally dominant organisms can vanish when ocean conditions shift beneath them. A single graptolite wasn't an individual animal, but a colony made of dozens to thousands of tiny zooids, each living in a small cup-like structure called a theca. These thecae connected into long branches called stipes, forming the distinctive shapes preserved in fossils. Early graptolites attached themselves to the seafloor like small bushes, but by the Ordovician, many species had evolved into free-floating plankton. This transition from bottom dwelling to open ocean drifting helped them spread across the world. Ocean currents carried graptolite colonies to every marine environment, from shallow coastal waters to deep ocean basins. Their global distribution and rapid evolution make them invaluable for dating rocks. Geologists can identify specific time periods based on which graptolite species appear in stone layers. The most fascinating aspect of graptolites is their evolutionary relationship to modern animals. They were hemichordates, related to acorn worms and pterobranchs still living in today's oceans. Pterobranchs are tiny creatures living in tubes, forming colonies that resemble miniature versions of graptolite structures. Scientists didn't confirm this connection until the 20th century, when they studied genetic patterns and soft tissue structures. Before that, paleontologists debated whether graptolites were algae, plants, or something entirely different. Their fossils were so simple, just dark carbon films showing branching patterns, that determining their biological nature took decades of research and multiple fossil discoveries with preserved soft parts. Graptolites succeeded because their body plan perfectly suited Paleozoic ocean conditions. Their colonies were lightweight, flexible, and efficient at capturing food particles from water. Many species developed elaborate branching patterns with multiple stipes extending outward like comb teeth. These patterns increased surface area for filter feeding without requiring additional building materials. Some colonies grew into spirals, others formed zigzagging ribbons, and still others created bushy clusters. Each shape represented an experiment in maximizing feeding efficiency while remaining buoyant in the water column. Natural selection rapidly refined these designs, producing new species with subtle modifications that improve performance in specific ocean conditions. One major evolutionary advantage was their ability to adapt quickly. Fossil records show dramatic changes in colony shape, theca size, and branching patterns over short geological periods. These rapid modifications let graptolites respond to environmental changes, shifts in water temperature, nutrient availability, ocean circulation patterns. When conditions changed, graptolite populations evolved new forms within thousands of years rather than millions. This evolutionary flexibility helped them weather several early extinction events without disappearing, maintaining their dominance through periods that eliminated less adaptable organisms. But their success depended on specific ocean conditions. Graptolites thrived in nutrient-rich waters with strong upwellings and stable plankton communities. As long as oceans circulated in predictable patterns, bringing nutrients up from deep waters and supporting abundant microscopic food, graptolites spread worldwide. Their decline began in the late Silurian and Devonian, when ocean chemistry and circulation patterns changed fundamentally. Reef systems expanded, altering current flows and nutrient distributions. Oxygen levels shifted in ways that disrupted plankton communities. New predators evolved in the open ocean, feeding on planktonic organisms including graptolite colonies. Competition played a crucial role in their downfall. Other planktonic animals, particularly early crustaceans, evolved more efficient filtering methods. Some developed harder bodies that resisted predation better than soft graptolite colonies. Others evolved faster reproduction rates or more versatile feeding strategies. Graptolites, with their simple cup and branch structures, couldn't match these innovations. Their colonies became less diverse, their geographic range contracted, and by the Devonian, many lineages were fading from open water ecosystems where they'd once dominated. The late Devonian extinction events delivered the final blow. Ocean circulation systems that had sustained graptolites for 100 million years broke down. Oxygen levels dropped in many regions, creating dead zones where filter feeders couldn't survive. Water temperatures fluctuated wildly. The stable, predictable oceans that graptolites required transformed into unstable environments where only the most adaptable organisms persisted. Most graptolite lineages vanished completely. Only one small group survived, ancestors of modern pterobranchs that retreated into protected microhabitats, abandoning the open ocean where their relatives had thrived for eons. Today's pterobranches are tiny animals living in tubes attached to rocks or shells in relatively deep water. They form small colonies, filter feed using tentacles, and rarely grow larger than a few millimeters. They bear little resemblance to their ancient ancestors that drifted as massive colonial ribbons through Paleozoic seas. Graptolites went from global dominance to near total extinction, surviving only as diminished remnants hiding in ecological corners. Their story illustrates a sobering evolutionary principle. Even overwhelming success provides no guarantee of long-term survival. Organisms perfectly adapted to specific conditions become vulnerable when those conditions change. Graptolites ruled Paleozoic oceans for 100 million years, then vanished almost completely when the oceans they knew ceased to exist.